in question 7, we have a graph of neutron number against proton number. In 7.1, we're to draw 4 arrows to show the sequence changing N and Z as poloniums transformed into lead. Well, it goes through alpha, beta minus, alpha, and for alpha decay, the neutron number, N, needs to go down by 2, and the proton number, Z, needs to go down by 2. For beta minus, the neutron number goes down by 1, and the proton number goes up by 1. So therefore, if we're doing an alpha decay, if we've got our graph like this with our little boxes, alpha will take N down by 2, 1, 2, and Z down by 2, 1, 2. So basically alpha is a line going like that. Beta takes N down by 1, Z up by 1, and down by 1, Z up by 1 is an arrow going like that for beta. So starting with our starting point down here, I'm not going to bother drawing the lines. We're going to go in reverse now, so we did an alpha, which takes us the opposite of this, so going up like this, 1, 2, that is our alpha. Then we have 2 reverse betas effectively going like that and like that, and then another alpha in reverse taking us that way. And this starting point, we have N of 132 and we have Z of 84. In 7.2, turn the page, we're to explain why there's an imbalance between proton and neutron numbers. Well, the electrostatic repulsive force acts between all the protons. It has infinite range, so every proton in the nucleus is repelling every other proton, albeit it falls away with distance. The strong force acts between all protons and neutrons. It is attractive up to around 3 femtometers, but repulsive when it gets below about 0.8 femtometers. By having more neutrons than protons, this adds strong force, which is attractive, without increasing the repulsive electrostatic force. In 7.3, we're asked to write an equation to represent the decay of lead-205 decaying by electron capture to become thallium. Well, with electron capture, the proton becomes a neutron. And what we have is we've got our 20582 lead, picks up an electron, which is 0 minus 1, and this stays as 205, this becomes 81, and it is now thallium, and there is also an electron neutrino. That keeps the lepton number balanced both sides. We have a lepton here, we have a lepton here. In 7.4, we're to explain the origin and location of 2 sources of radiation. Well, electrons will fall from higher energy levels to lower energy levels vacated by the orbiting electrons. They release electromagnetic radiation as they do. The nucleus will also release gamma radiation as it de-excites. In 7.5, we're to explain why metastable form of technetium-99 is suitable for use in medical diagnosis. Well, it only emits gamma. This is a weakly ionizing radiation, so it can escape the body to be detected and do minimal damage on the way. The half-life of technetium-99 is around 6 hours. That's long enough to carry out the procedure, but short enough to not leave the patient radioactive for too long.